Welcome back to the Explainer. Today, we're diving into something really cool, the hidden syntax tricks of assigning values in Java. Now, you might think you already know the drill when it comes to just typing a number or a letter into your code, right? But it turns out Java has some incredibly clever hacks built directly into its core. We're going to demystify Java literals today, and we'll explore the surprising flexibility and, honestly, sometimes the strict rigidity of how Java actually handles the raw data you feed it. So here's our roadmap for this explainer. First, defining a literal. Second, integer bases and formats. Third, readability in scientific notation. Fourth, the strict Boolean rule. And fifth, character math and strings.
All right, let's jump right into section 1, defining a literal. At its core, what is a literal? Well, it's exactly what it sounds like. It's the fixed data value assigned directly in your code. We're talking about the raw data you're typing out, like the number 9 or 8, rather than the variables that hold them. They are literally their values. It's a fundamental concept for sure, but it really sets the stage for the clever syntactical tricks Java allows under the hood.
Moving right along to section 2, integer bases and formats.
Java is actually surprisingly flexible when you peek under the hood. Beyond your standard base 10 decimals, you can natively work in binary just by adding a 0b prefix. It's that easy. You type 0b, 101, and the compiler parses it perfectly, outputting a 5. And what if you need hexadecimal? Just use a 0x prefix. Typing 0x7e seamlessly compiles to 126, and you don't have to write any manual base conversion logic at all.
Okay, section 3, readability in scientific notation.
We've all been there, right? Staring at a screen, squinting, trying to figure out if you just typed 1 million, 10 million, or 100 million. Whether it's a massive account number or just a test value, a solid wall of zeros is a total headache. Well, to solve this, Java actually allows you to place underscores directly between numbers. So you get this incredibly clean format. The best part? The compiler completely ignores the underscores. They exist purely as a visual aid to make counting those zeros absolutely effortless for us developers.
But it's not just about what looks good to our eyes. Java literals also do some serious heavy lifting with formatting for memory. For instance, if you declare a floating point variable, like a double, and then you try to assign a standard integer literal to it, say the number 56, what do you think happens? You actually don't get an error. Java automatically converts that integer and saves it as a double for you. It literally just handles the translation seamlessly right in the background.
And for truly massive numbers, you don't even have to type out the zeros at all. By using epsilon e notation, typing 12e10 directly into your code represents 12 times 10 to the 10th power. The compiler just takes care of the internal parsing for you.
Which brings us to section 4, the strict Boolean rule.
Now, I want to pose a question directly to you. If you're coming over from other programming languages, you might be pretty accustomed to a specific shortcut. Can you use a 1 and a 0 to represent true and false in Java? Take a second. What do you assume the compiler is going to do here? Well, if you guessed yes, you are in for a bit of a surprise. If you try to assign a 1 to a Boolean variable, Java immediately throws a compilation error, telling you that an int cannot be converted to Boolean. Unlike C or Python, Java is incredibly strict here. It literally requires you to use the actual words true and false. No shortcuts allowed.
All right, let's move to our final topic, section 5, character math and strings.
Listen to this quote straight from our source material. Basically, character can be also treated as integer. We can actually perform operations. This is so fascinating to me. A single character in Java, like a lowercase a inside single quotes, actually hides this crazy mathematical potential. Let's see how this plays out in practice.
Let's actually trace this out step by step. Say we assign the literal lowercase a to a char variable. Then we apply the ++ increment operator to it. Because Java treats character literals as their underlying integer values in the Unicode table, applying a mathematical operator literally increments the letter itself. Print it out, and the output is a lowercase b. It is literal character math. How cool is that?
And that brings us to the end of today's explainer, but I want to leave you with a thought.
We know that typing hello world constitutes a string literal in Java. But if single characters are hiding this secret integer math that literally lets us increment the alphabet, what kind of hidden powers in behind-the-scenes mechanics do string literals hold? How on earth does Java manage a whole sequence of these mathematically capable characters? It's definitely something to keep chewing on as you continue exploring Java's architecture. Thanks so much for joining me on this deep dive into Java literals. Keep exploring, and I'll see you in the next explainer.